If you have any questions, any comments, don't be shy. You're welcome. Any questions? Any questions?
We don't have today topic to discuss.
Sorry?
Don't we have any topic today to discuss?
Yes, we have, but we have covered all topics for the exam. I have prepared some medium or hard problems, but probably if you have any questions, then I'm ready to answer them. That's completely okay. So basically, we have solved at least one problem dedicated for each subject, for each topic. So basically, we're a little bit free. Okay. Just think a little bit. Maybe you have any questions. Okay, let's solve some more examples. Pricing European claims. Okay, let's discuss pricing European claims. European claims. Imagine that here we are at t equal to 0, and that specified fixed time moment t, I pay you, I give you one share. Yeah, I pay you ST under condition. So I give you one share, basically. What does it mean? Pay ST. Yeah, I give you one share. Let's say if the share price, if ST is less than 100. Okay, I give you one share under some condition. So that will happen here. So basically, the price of this contract at time t is easy to calculate. That's just ST multiplied by indicator that ST is less than 100. So I pay you one share if the share price is low, and I give you nothing if the share price is high. And my question is, what is the fair price of this contract at time 0? So that's our exercise. Let's recall. Yeah, and I suppose that we are in the framework of Black-Scholes model. Yeah, because there are some other extensions. Let's suppose that we are inside the Black-Scholes model. That's a small world, but that's already enough to calculate the price of the asset. Okay, if you remember our previous story about Black-Scholes model, and in Black-Scholes model we have the share price ST. That is either we have two explicit formulas. We have F0 times exponent mu t times exponent sigma wt minus sigma squared over 2 times t. We have st expressed alternatively, like exponent rt multiplied by exponent, and here we have wt star minus sigma squared over 2 times t. We have also bond price, bt, that is b0 times exponent rt. And we have some strange probability measure p star under probability p star. ST divided by exponent RT, so discounted prices of both assets are martingales. So discounted prices, if I just divide ST by exponent RT and BT by exponent RT, and any other asset price is also a martingale xt divided by exponent RT. Everything is a martingale. So they are all martingales. So that's a very useful probability measure P star. We have a very simple relationships if we use this probability measure P star. And hence our x0 is, because this is a martingale, so x0 is an expected value with respect to this probability measure P star of xt divided by exponent RT. Hence, to calculate x0, we just need to calculate risk neutral expected value star of xt, and we need to discount it to multiply by exponent minus RT. So the problem of pricing European claims in theory boils down to the calculation of expected value under this strange risk neutral probability measure P star. We have no explicit expression for P star. We don't know how to describe it in a simple way, but we have one process, the probabilistic characteristics of which are known under P star. Yeah, we say that WT star is a winner process under P star, and that's enough to calculate this expected value. This is all we need to know. All we need to know to calculate this expected value star.
Is there is actually a formula for our value of the stock at some point t, at some time t, like?
Yes, the share price is, we have two formulas. Both formulas are correct. One uses WT and the other one uses WT star. Yes, we have the share price at time moment t, and the Black-Scholes model is governed by this equation.
Okay, I'm not sure like what's the difference between xt and st. I mean, I see it, but I mean more in the some more common
ST
sense
and
rather.
XT, what's the difference?
Yeah.
ST and XT. Okay. We have a bond. Yeah. So, okay, let's start with two basic assets. We have two basic assets. The share price. So that's a share price. Share price. This is a bond price. Bond price. And we have described our third asset. We have introduced one more asset in the Black-Scholes model. We have said, okay, imagine that I promise at time moment t, big T, at time moment big T, I will give you one share, if ST is less than 100. And I give you nothing if this condition is violated. And this promise may be traded. So you can, so I've promised this to you, but you may say, okay, to some other guy, Boris has promised me to give me one share at time moment big T. I don't know. Let's say that big T is 1 year later. Mm-hmm. Yeah, 1 year later, Boris has promised me to pay me one share under some condition, and you may trade this financial asset. Yeah, you may go to your friend and say, I need money now. This is a promise from Boris. Can you pay me something for it? Obviously, this promise has a price, because you either receive zero, either receive a positive amount of money. So this has a price. Yeah, this is an asset that has a positive price. Let's imagine that you believe my promise. So the only risk part of this asset, if if the price of a share is very high, then this promise is worthless. Yeah, because if the share price is high, I have no obligations, and hence you may trade this promise. And XT is the price of this promise. So XT is the price of this claim. So basically we have three assets. One asset is a riskless bond price that just goes up. Woo. So this is T, this is BT. Yeah, we have a riskless interest rate, and that just goes up. We have risky share, and we have an asset that is obviously it's linked to the share price. If the share price is high, if ST is high, XT is low. Yeah, imagine that at some moment of time here. Yeah, imagine at some moment of time here. Imagine that as T is very big, so that basically will mean that XT at this moment of time is very low. Yeah. If you see that the share price is high, then my promise is worthless. Yes, there is a small probability that the share price will go down and I will need to pay something. But if at some moment ST is high, then X is zero. And vice versa. If, let's say, ST at some moment time is 80, then probably XT has a positive value. Yeah. So this the price of my financial claim. Yeah, this is a financial asset that's not a share. Yeah, that's not a bond, but that's a asset that can be traded. Okay.
Okay.
And our goal is to find X0. And if you can find X0, you can also search for the general formula XT. But if you can find X0, then just as a change of time to. But by the way, let's see how calculate XT if you know X0. Yeah, the important thing is to understand that we have three assets. The share price discounted. We have three assets: the share price, the bond price, and the price of this tranche of my promise. Yeah. And under probability measure P, all three discounted prices are martingales. And it is possible to say that B0 is expected value of BT multiplied by exponent minus RT, but this is trivial because if you divide BT by exponent RT, you will get B0. Yeah, if you just divide this part, you will get B0. So that's true, but that's obvious. Yeah, that's true. So this is true, and for share that's also true. S0 is just expected value of ST multiplied by exponent of minus RT by discounting factor. So for all assets, we have the relation, the martingale type relation. Okay, we are interested in this one. So how much should you pay me in exchange for my promise? Okay, let's calculate it. So X0 as exponent minus RT times expected value star. What do you get? You get ST under condition that ST is no, is less than 100. Okay, let's simplify everything we have. Let's plug in ST. Let's plug in the formula for ST, then just S0 times exponent RT times exponent sigma WT star minus sigma squared over 2 times T. Okay, we just plug in everything. Expected value star S0, exponent RT, exponent WT star, exponent minus sigma squared over 2 times T, times indicator that T is less than 100. Okay, now we move all non-random quantities outside of the expected value. That is non-random. That is non-random. Hence, we will have S0 multiplied by exponent minus sigma squared over 2 times T times expected value star over exponent of sigma WT star multiplied by indicator that ST is less than 100. Okay, let's focus on this part. Let's first simplify the event, the happy event A, when I will give you a share. Yeah, this event A, ST is less than 100. So once again, I plug in everything I know about ST to simplify this event. S0 times rho exponent RT exponent sigma WT star minus sigma squared over 2 times T is less than 100. I take logarithm inside expected inside this event. I take the logarithm of both sides of the inequality. So I take log of both sides. I will have logarithm as 0 plus RT plus sigma WT star minus sigma squared over 2 times T is less than log of 100. Okay. Basically, that give me WT star should be less than, because the only random variable is WT star. Yeah, why I'm transforming it? Because that is the only random quantity that is random. Other quantities are non-random. Yeah, I have only one random quantity, WT star. So WT star is equal to log 100 minus log S0 minus RT plus sigma squared over 2 times T divided by sigma. Let's denote this big ugly fraction by some letter. Let's call this letter, let it be beta. Okay, so our event is basically is described by WT star is less than beta. Beta is this big fraction. Okay, so let's go back to our x0. Our x0 is S0 times exponent minus sigma squared over 2 times T, yeah, multiplied by expected value star of exponent sigma WT star multiplied by indicator that WT star is less than beta. Let's go on. let's go on. Okay, how to calculate expected value? Probably, I strongly believe that there is a tricky way to do this. So I believe that there is a tricky way with martingales to do this, but I don't know it. I know a samurai way how to calculate expected value, take an integral. So I believe, yeah, like this. I believe that there is a tricky way to do this, something very beautiful, but I don't know it. I know a dumb way to do this. I believe there is a tricky way to do this. I don't know it. I just use a samurai method. How to calculate expected value of, let's say, w squared. So you need to integrate from minus infinity up to infinity w squared times the density function. Yeah, so this is a PDF. So I will use the samurai method, just how to calculate expected value, integrate. But I believe there is a tricky way. I don't know it. But I believe that it's possible to construct some martingale with this somehow to transform somehow this value into a martingale and to obtain directly. Okay, let's be a brave samurai and let's integrate. If you remember WT star under probability measure P star, that's a winner process. So it has normal distribution with mean 0 and variance T. So basically the PDF of W star is, so let's emit the star. Let's emit the star. PDF of W, PDF W at the point, PDF of W star at the point W is given by 1 over square root of 2 pi times T multiplied by exponent minus W squared over 2T. So that's the formula for the PDF probability density function of a normal variable with mean 0 and expected value T. Okay, let's continue. So let's be brave and let's calculate the expected value through integration. So it says as 0 exponent minus sigma squared over 2 times T times integral from minus infinity up to plus infinity exponent of sigma W times indicator that W is less than beta times 1 over square root of 2 pi T multiplied by exponent of minus W squared over 2T dW. So that's a honest integral to calculate this expected value. This is the PDF of normal 0T. Normal 0T. Okay, so what shall we do? We shall we shall take this term, take that term, and bring them together. We have 3 exponents. We will bring them together. Okay, what do I have? S0 times integral from minus infinity up to plus infinity, indicator that W is less than beta, or 1 over square root of 2 pi t times big exponent dw. I have minus 2t. What will happen? W squared minus 2 sigma w t plus sigma squared t squared. And I see a miracle happens. I have a complete square. Inside I have a completed square. I just need to see that this is expression of the form a minus b squared. So it says 0 times integral from minus infinity up to plus infinity. Oh, by the way, I just need so this indicator, so let's simplify the indicator, yeah? Indicator of w less than beta is just a very simple function. It is 0 if w is less than beta, and it's 1, oh, sorry, vice versa. It is 1 if w is less than beta, and it's 0 if w is not less than beta. Hence, I integrate nothing. My density is multiplied by 0 for big values of w. Hence, I may just write as 0 times integral from minus infinity up to beta. 1 over square root of 2 pi t exponent. What will I have here? Minus w minus, I think, sigma t squared over 2t dw. Okay, let's look inside. Let's give this integral a probabilistic interpretation. Yeah, let's interpret this integral in probabilistic terms. What do I see here? What do I see here? That's a PDF. That's a PDF of a normal random variable with strange expected value. It's like mu, yeah? It's like expected value. And this is like sigma squared, yeah? So let's recall the classic formula, probably. 1 over the classic formula is 1 over square root of 2 pi sigma squared, exponent minus x minus mu squared over 2 sigma squared. So I see a complete coincidence with a PDF of a normal random variable, but not standard. Strange random variable, really strange. That's a really strange random variable, but okay, that's a PDF. PDF of a random variable that is normal, that has some strange expected value, sigma t, and strange variance, t. Okay, so basically, if you integrate the density up to a point beta, you get S0 times probability that these strange random variable is less than beta. Because when you integrate probability density function, you obtain probability of the corresponding event. Let's standardize our random variable. To standardize a random variable, probably you remember that if y it has normal distribution mu and the sigma squared, to standardize it, you just take y minus expected value of y, you divide by square root of variance of y, and you will have a standard normal random variable. So I do the same trick here. I standardize my random variable. So I will obtain probability that standard normal is less than beta minus sigma t over divided by square root of t. And that is S0 times the cumulative distribution function at this point. Okay, and now let's recall the value of beta. I have the value of beta, I think, on the previous page, and that is beta. Let's copy the value of beta. So I have a 0 times f minus what should I subtract? I should subtract minus sigma t. No. I should subtract. How it's better to say? I should subtract minus sigma squared over t, because I have already divided by sigma, and divide additionally by sigma square root of t. Okay, and I hope that's the last thing we can do. S0 times, so our initial fair price of the asset is a standard normal CDF, cumulative distribution function, CDF of a standard normal, evaluated at the point log 100 minus log S0 minus RT minus sigma square root over 2 times t divided by sigma square root of t. And that's our final answer. So that's a fair price of an asset at time 0. Let's check whether it coincides with our definition. Yeah, with our intuition, not definition, without intuition. We have discussed that if ST is high, then we have almost 0 chances to get the share I have promised. Because if the share price is high, then the probability that condition will be satisfied is low, and basically that means with high share price, this financial claim should have low price. Okay, let's check that this is satisfied. Let's imagine that S0 is very high. Let's imagine that S0 is very high. If S0 is very high, then this value is high. Logarithm of S0 is high, and this value inside CDF is very negative. But if you remember, so it seems at first that we have something high multiplied by something close to 0. But if you remember, the normal CDF is very low for negative values. If you just take minus 10, if you take minus 10 or something like minus 10 is enough to have the value of f almost 0. So f decays to 0 much faster than S0 will grow. Hence, indeed, this value is approximately 0 for big values of S0. Yeah, so that coincides with our intuition that for big value of S0, we should have lower x0, because the function f decays very fast when its argument goes to negative numbers big by absolute value. Okay, as I promised, let's change time to see how this formula changes if I would like to calculate xt, not x0, but xt. So what will change if I need to calculate xt? So that is the formula for the price at t equal to 0. This is time moment t. That is the price here. And what is the price at time moment t? What is the price xt? But basically, if you introduce a new timeline, we introduce new timeline, we say, okay, let it be this t prime. This is t prime equal to 0. That is t prime is equal to t minus t, big T minus small t. So basically, if you need to price these claim my promise at intermediate moment t, we can just introduce new timeline, and we can say that basically xt, we just take st, yeah, we just think that this is our starting moment of time, times f log 100 minus log st minus, and I need to use new timeline, so I need to think how much time is ahead of time moment t before the final moment of execution of promise will arrive. And hence here I write r times big T minus small t. So I just replace my old time by new timeline, minus sigma square root over 2 times big T minus small t. So I just count the time that is ahead of me when I start my new timeline at time moment 0. And here I will have sigma times square root of big T minus small t. Okay, that's the general pricing formula, and it depends on ST, on time up to the execution, and we see that if time up to the execution, if the time remaining is very small, basically what will happen if the time remaining to the execution is very small? Basically, all these terms will disappear. All these terms will disappear, yeah? If t minus t is very small, and hence the only important factor will be whether st is bigger than 100 or less than 100, and that's once again is consistent with our intuition. Okay, any questions? So we have calculated the price of a financial claim using hard integral, using samurai way to calculate integral. Any questions? Okay, let's continue. Let's solve some more pricing problems. I understand that this was rather hard because of the samurai way to calculate expected value, but I don't know a more simple way, I would be happy to find it, but I don't know it. Okay. Let's continue. Okay, let's solve some stochastic differential equations. Let's exercise. Let's recap the Ito's lemma, stochastic differential equations, how to solve them. Okay, let's consider the stochastic differential equation. dRT is 4RT dt plus 7dWt with some initial condition that are 0 is 1. This type of stochastic differential equation can be used to model interest rate, obviously with other parameters. So parameters 4, 7, and the initial condition are just out of the blue. But the structure of this equation can be used to model interest rates. Okay, so, and here I will show you the idea of a standard way how to solve stochastic differential equations and maybe ordinary differential equations. So, step 1, solve a more simple equation. Solve a more simple equation. And then modify the solution of a simple equation to obtain the solution of original equation. So that's a general idea. It's a general trick that is used in many situations. Maybe that's the most general mathematical trick ever. So when you have a hard problem, simplify it, solve a simplified problem, and enjoy. Okay, imagine that I need to start to solve this equation. Okay, let's do step 1. Step 1. I remember more or less how to solve deterministic differential equations. Okay, so let's consider the simplified equation. Let's remove randomness from this equation. Okay, let's remove randomness from this equation. Okay, so I will consider the equation d qt is 4qt times dt. So I've just removed dwt by 7. Yeah, I have just removed this term, and I have replaced r by q because r is the solution to the original hard equation, and q is the solution of a simplified equation. So why I have changed the name of the letter to distinguish R and Q. Q is the solution of a simplified equation. Okay, let's solve it. This equation is not hard. We just say dqt divided by qt is 4 dt. We integrate. We say that log qt is equal to 4t plus constant, hence qt is exponent of 4t times some other constant d, and I have solved the simplified equation. Yeah, that's a solution of a simplified equation of a deterministic differential equation, but probably I can modify it to obtain the solution of my equation. Okay, how to modify it? Basically, it's a little bit of an art how to modify it. But two standard tricks are modify by adding something or modify by multiplying by something. Okay, probably two standard tricks are the following. So how to step 2. Now we have step 2. We modify simplified solution. Simplified solution. There are many ways to modify, how to modify. Sometimes we can add qt plus something, yeah, or qt modified by, multiplied by bt. There are other ways. You may apply some transformation, yeah, you may say that you apply some h of qt, or maybe even h, or even the function of qt and t. So there are many ways to modify this solution, but probably the most frequent one is multiplication by another process. Okay, let's choose that way. That's a little bit of an art. It is not always possible to solve stochastic differential equations explicitly, so that's a little bit of an art, but let's follow this strategy. We say that RT is just QT multiplied by BT, and we know that if we plug in into dRT, that should be equal to 4RT times dt plus 7 dWt. And if I plug in QT, then dQt is 4QT dt. This is satisfied by design. It is by design. QT, we know, let's choose one of the solutions. Let's say that is just exponent of 4t. Okay, so my RT is just QT times, exponent of 4t multiplied to BT. And now the only thing that remains is to find BT. Okay, the only thing that remains is to find BT. Let's apply it as lemma. Apply it as lemma. It as lemma. Let's recap it as lemma. It as lemma has the following form. Basically, use second order Taylor expansion, and replace dt by multiplied by dt by 0, dt times dwt by 0, and dwt times dwt by dt. So we have it as lemma. We have two steps in it as lemma. Okay. So let's apply it as lemma to calculate dRT. What is dRT? So first order Taylor expansion. 4 exponent 4t times bt times. Okay, let me write in abstract letters first and then in general. Okay, my RT is just a function of t and bt. So dRT is h prime with respect to t times dt plus h prime with respect to b times dbt. That's a first order Taylor expansion. Plus I add the second order Taylor expansion. H prime prime with respect to t times dt plus twice h prime prime with respect to b to t times dt times dbt plus h prime prime with respect to b times dbt times dbt. That's a second order Taylor expansion. Okay, let's simplify this Taylor expansion by using this mnemonic rule that dt times dt is 0, dt times dwt is 0, dwt times dwt is dt. Okay, so what will I get? I will get h prime with respect to t times dt plus h prime with respect to b times dbt plus 1 over 2 h prime prime with respect to tt times 0 plus twice h prime prime with respect to b to t times 0. I use mnemonic rule that dt times anything is 0 plus h prime prime with respect to b times dbt squared. Okay, but I know the expression for RT. So I just use this expression for RT. I have 4 exponent of 4t times bt times dt plus exponent of 4t times dbt plus 0 because in my case this h prime prime with respect to b is 0. RT in my case is exponent of 4t times bt. Okay, let's plug in the value of dbt. What is dbt? I have dRT is 4 exponent 4 t times bt dt plus exponent of 4t times dbt. And what do I know? I know that that's one expression for dRT. From the other hand, I should have dRT is equal to 4RT dt plus 7dWt, and RT is exponent of 4t times bt. So basically I see that these two terms, that term is exactly equal to this one. These two terms are equal. The left-hand side is the same. So I see that exponent of 4t times dbt should be equal to 7 times dwt. Okay, and I need to find bt. Yeah, let's recall that we need to find bt. Let's copy this equation in shorthand notation. and we will recover its full form in a moment. So dBT is equal to 7 exponent of minus 4t times dWt. That's a shorthand notation. Short notation. And hence we can recover the long notation. BT is equal to B0 plus integral from 0 to T7 times exponent minus 4U dWu. Okay, we have found everything. Now we just can write that RT is exponent 4t times this B0 plus integral from 0 to 7 from 0 to T 7 exponent of minus 4u dWu. And we have initial condition. Initial condition was R0 is 1. So R0 is 1 times B0 plus integral from 0 to 0 dWu. Hence, we see that B0 is also 1. And our final expression for this RT, normally that can be a model of an interest rate exponent, but with other parameters. 4t is explosive, but with negative value inside instead of 4, that it's a good model for interest rate R. Okay, 4t times 1 plus integral from 0 to t 7 exponent of minus 4u dWu. Okay, that's a solution to our stochastic differential equation. We have an integral that can't be simplified, that often happens in stochastic differential equation world, that some integrals can't be simplified, but that's completely okay. We can easily simulate it. Yeah, we can easily simulate it on a computer. We can calculate probabilities. We can calculate expected values. So, for example, let's calculate expected value of RT, or let's calculate variance of RT in this model. Yeah. So to understand that this expression allows us to easily calculate characteristics of this stochastic process. For example, let's calculate expected value of RT. That will be exponent of 4t, because that's a non-random multiplied by 1 plus expected value of stochastic integral. And who remembers the expected value of a stochastic integral? Who remembers one of the properties of stochastic integral? The expected value of stochastic integral is equal to
0.
Yeah, that's great. Okay. Yeah. Okay, what about variance? So that's about expected value. What about variance? If we calculate variance of RT, once again, the first quantity is non-random. So it will go outside of the variance with square sign. I will get variance of integral 1 plus integral from 0 to t 7 exponent minus 4u dWu. Okay, we recall that constants do not influence variance. We can just remove it because adding constant shifts the expected value, but has no influence on the variance. Okay, we have exponent of 8t multiplied by variance of a stochastic integral. And we have ethers isometry property that says how to calculate the variance of a stochastic integral. Who remembers how to calculate what was the property variance of integral from 0 to t? AU dWu is just the ordinary integral from 0 to t du. And here I need to take AU squared on the expected value. So this property is called ethers isometry. Ethers isometry. And that's enough to calculate everything. So that's exponent of 8t, integral from 0 to t 49. Okay, I will square it explicitly. 7 exponent 7 exponent of minus 4u squared du by ethers isometry. And we are brave enough to calculate all characteristics of this process. That will be integral from 0 to t 49 exponent of minus 8u du. We got exponent of 8t 49 exponent of minus 8u divided by minus 8, and u should change from 0 up to t, and hence we've got our final answer, 49 exponent 8t multiplied or divided by minus 8 multiplied by exponent of minus 8t minus 1. Yeah, exponent of 0 is minus 1. And in this case, yes, because 4 is positive, this process has an explosive expected value. The expected value goes up, and the variance goes up too. Yeah, because if I simplify, I will get something like, what will I get if I simplify this expression? But I think I have enough place on this page. I need only one line. It will be 49 over 8 times exponent of 8t minus 49 over 8. Yeah, and I see that the variance also goes up to infinity, and so my constants are not corresponding to an interest rate, because interest rate should be between, basically should be close to 0. But this type of a stochastic differential equation with other parameters, with some small negative number instead of minus 4, some other number, some small numbers instead of 7, can be used to model interest rate. And we have discussed how to solve this stochastic differential equation using quite general approach. This approach is quite general. If you can't solve a stochastic differential equation, solve a more simple one and modify the solution. Probably, if you have studied ordinary differential equations, I don't know whether this course is compulsory now. It was compulsory in high school of economics some years ago, but now I think it either absent, either can be chosen, but not always chosen. And the technique like variation of constant method was presented during this course, and basically variation of constant, if you have heard of this method, I don't know. This method basically is the same idea. What is a variation of constant? You solve a simple differential equation and you replace constant by a function of t, so you just multiply the simplified solution by a perturbation factor. Okay, any questions? We have solved, I think, 2 hard problems.
So is it true that dbt squared is equal to dt?
No, I don't know. dbt squared is not equal to dt. Let's calculate dbt squared. We don't need it because it's multiplied by the second derivative with respect to b, and the second derivative with respect to b here is 0. We have no b squared. So it is killed by 0 factor before. Let's calculate dbt. That's a good question and simple. Okay, let's calculate dbt times dbt. But we have the expression for dbt. It's, let me look once again at the beginning of the problem. So it's, we have obtained the, where it is, dbt. Yeah, we have here the expression for dbt. Yeah. If we will calculate it, calculate this value squared, what will we get? If we square this value, we will get 49 exponent minus 8t times dwt squared, and it will be 49 exponent minus 8t times dt. Almost right. You have a factor before dt. Our rule for the Ito's lemma is that dwt times dwt for Wiener process, you have dt, but bt is not a Wiener process. It's just the name of a process. It's not a Wiener process. Yeah, and so that's a little bit different than dt, but basically you are right. It's close to dt. It's dt multiplied by some factor. But we don't need this value because our process, why do we do not need it? This is our function h of t and bt, yeah? And if I take the second, so with respect to bt, it's linear function, yeah? It has a nonlinear part with respect to time, it's exponent of 4t. But if you look at this function and you think of this function as a function of b, it's a linear function, and h prime prime with respect to b is absent. There are no quadratic terms or cubic terms as if we think that that is a function as a function of b. Yeah. So this guy is 0. This guy is 0, and so I multiply it by, and that is 49. Okay, so that's not exactly dt, but it's proportional to dt. So it's proportional to dt. So that is times dt. That's a good question. I like this question. Any other questions? Okay, let's solve something. We have, I think, 10 minutes or something like this. Yeah, I think
Yes.
we have 10 minutes. Yeah.
I have a question.
Mhm.
It's not about what we discussed today. It's about in general. I missed a few lessons, and I'm trying to catch up with the program. May you recommend some books or like textbooks I can read with practical examples of tasks and how to solve them?
That's the problem. Stochastic calculus is a rather tough subject. So from mathematical viewpoint, it's very hard. So if you are trying to do stochastic calculus rigorously, that's the problem. We are trying to provide we are trying to be as gentle as possible. But believe me, if you are trying to do this rigorously, then it takes enormous amount of time. So how to practice? You can solve. So so basically, what are good books? I think good books is, but even the name of the author suggests that the author, the name of the author is Zastavnyak. Yeah, you see, Zastavnyak. Yeah, basic stochastic processes. So it's a basic stochastic processes. I think that's a good book with some worked examples. The classic reference is Shreve, but I think that's more harder. There are 2 volumes by Shreve. I think it's called Stochastic Calculus with Financial Applications. Stochastic Calculus. Yeah, I don't remember, but it's 2-volume books there. So if you Google Shreve, 2 volumes, I think it's called Stochastic Calculus. If you are more oriented on how to solve problems on the exam, then the advice is a little bit different. I don't know your goal. So would you like just to deepen your knowledge and to study more and more of stochastic calculus, or you are just trying what should I do to prepare for an exam? So I advise you to look in the past exams collection. Yeah, and there are 2 of them. One for our course, specially designed, and the other for the master course at International College of Economics and Finance. But basically there, the stochastic calculus course, it's oriented toward master students, but it's very short. It's much shorter than our course. So basically, the level of the course coincides with the level of our bachelor course, because we are studying more than 6 weeks, and there the course takes, that's a crash course, and it's a 6 weeks course, 7 weeks course, something like this. So it's much shorter than our course. So basically the level of the exam, so you have 2 collections. So there is a link in the Telegram chat. So basically you have 2 past exams collection. There are partial answers. If you are trying to solve some past exams and the answer is missing, you can ask a question in the chat. So I'm trying to solve from the past exam collection number 7. I've got that result. Is it okay? And we will try to answer. So if your question is about broadening, is about what shall I read to study stochastic calculus by myself? Okay, so I think the good book is Zastavnyak and the classic one is by Shreve. And if you are just preparing for the exam, that probably another way is to solve past exams. There are enough of past exams to practice.
Great, thank you. Yes. I just want to solve a little more problems to understand it, the course better. So yeah, I will read the Stavniak's books and solve previous year's exam. Thank you.
Okay. Okay, I think that's a good moment to stop. We have 3 minutes, but I don't know a problem that that is interesting and can be solved in 3 minutes. So let's stop here. Thank you very much. Once again, don't be afraid to ask questions in the chat. It's designed for your questions. So if you are saying, I'm preparing, and every teacher will be happy if there are questions in the chat. So that's, be brave. Okay, thank you very much.
Okay, thank you.
Bye-bye.
Thank you. Bye.